Auzubillahiminash-shaytanir-rajim. Bismillahir-Rahmanir-Rahim. My name is Nabira and I am the student of University of Management and Technology. The topic I am going to present is Kevlar. Let's see first of all table of contents that include abstract, introduction, chemical structure, methods for Kevlar production, process description, types of spinning, objectives of Kevlar and properties, superb properties of Kevlar, advantages and disadvantages, uses and applications, conclusion, and then references. First of all, I will describe abstract. Kevlar is high modulus para-aramid synthetic fiber. This fiber is one of the heaviest fiber of all the time. In this paper, there are some discussions about the Kevlar's properties, function, and uses. Although in the past there were some research work had done and paper also been published, but this paper just simplifies the things as well. Then I will describe introduction. Kevlar is a synthetic fiber that belongs to the family of aromatic polyamides. Woolly aromatic polyamides set themselves apart from other man-made fibers due to their special qualities and distinctive chemical makeup. High strength, high modulus, toughness, and thermal stability combine in a special way in Kevlar. It was created for complex industrial and high-tech applications. Kevlar is currently made in a variety of forms to accommodate a wide range of end products. Then here is chemical structure of Kevlar. Kevlar is an aramid fiber, which is short for the aromatic polyamides, in which the molecules arrange themselves into lengthy, sharply aligned chains. To take use of these remarkable qualities, the fiber can be spun or woven into mats or fabrics. A condensation reaction between an amine and acid chloride produces Kevlar, just like this. The Kevlar chains tend to form primarily planar sheets and are relatively rigid, much like silk. The benzene rings para-orientation is blamed for this. The chain of Kevlar link together through hydrogen bonds to form a sheet with an extremely high tensile strength when it is spun. Also because of the sheets radical stacking, which resemble a wheel spoke, additional interaction between the face-to-face aromatic groups on neighboring sheets are possible. Then we have the methods for the Kevlar production. Kevlar production is expensive because of the difficulties arising from using concentrated sulfuric acid needed to keep the water-insoluble polymer in solution during its synthesis and spinning. Process of Kevlar manufacturing. The process includes that, first of all, paraphenylene diamine is mixed with terephtholyl chloride. A condensation polymerization with lithium chloride at low temperature occurs. Then HCl is added into this mixture. Liquid crystal polymer is formed that passed from the dry jet wet spinning, drying at more than 300 degrees centigrade Celsius at 15 to 20 draw ratio, and finally staple fiber of Kevlar is produced. The two raw materials, paraphenylene diamine and terephtholyl chloride, will undergo low temperature polycondensation in alkyl amide solvent like dimethyl acetamide. The polymer from this reaction system is isolated by precipitation with water, neutralized, and subsequently washed and dried. The polymer and sulfuric acid solution will be subjected to dry jet wet spinning for producing Kevlar fiber or filament yarn. The Kevlar polymer decomposes in heat before reaching the melt temperature, so melt spinning is not used. Several grades of Kevlar are available. The first one is Kevlar K29. It is used in industrial applications such as cables, asbestos replacement, brake lining, and body armor. The second one is Kevlar K49. It is high modulus used in cable and drop products. Third one is Kevlar K100. It is colored version of Kevlar. The fourth one is Kevlar K119. It has higher elongation, flexible, and more fatigue resistant. The fifth one is Kevlar K129. It is higher tenacity for ballistic application. The sixth one is Kevlar AP. It has 15% higher tensile strength than Kevlar 29. And the last one is Kevlar KM2. It has enhanced ballistic resistance for armor applications. The ultraviolet component of sunlight degrades and decomposes Kevlar, a problem known as UV degradation, and so it is rarely used outdoor without protection against. Then I will describe the process description. Most synthetic and cellulosic manufactured fibers are manufactured by extrusion, forcing a thick viscous liquid through the tiny holes of a device called as spinet to form continuous filament of semi-solid polymer. In their initial state, The fiber-forming polymers are solid and therefore must be first converted into a fluid state of extrusion. This is usually achieved by melting if the polymers are thermoplastic synthetics or by dissolving them in a suitable solvent if they are non-thermoplastic cellulosic. If they cannot be dissolved or melted directly, they must be chemically treated to form soluble or thermoplastic derivatives. Recent technologies have been developed for some specialty fibers made up of polymers that do not melt, dissolve, or form appropriate derivatives. For these materials, the small fluid molecules are mixed and reacted to form the otherwise interactable polymers during the extrusion process. Next, I will describe the machinery that is used during the production of Kevlar. The first machinery is spinet. Spinet just belongs to the or similar match with the bathroom shower head. A spinet may have from one to several hundred holes. The tiny openings are very sensitive to impurities and corrosion. The liquid feeding them must be carefully filtered, and in some cases, the spinet must be made from very expensive corrosion resistant metal. Maintenance is also critical, and spinet must be removed and cleaned on a regular basis to prevent clogging. As the filament emerge from the holes in the spinet, the liquid polymer is converted first into a rubbery state and then solidified. This process of extrusion and solidification of endless filament is called spinning, not to be confused with the textile operation of the same name, where short pieces of staple fibers are twisted into yarn. There are four methods of spinning filament of manufactured fiber: wet, dry, melt, and gel spinning. The first one is wet spinning. Wet spinning is the oldest process. It is used for the fiber forming substances that have been dissolved in a solvent. The spinet are submerged in a chemical bath, and as the filament emerge, they precipitate from solution and solidify. The process begins by dissolving polymer chips in a suitable organic solvent, such as formamide, dimethyl acetamide or acetone, or in a weak inorganic acid, such as zinc chloride or aqueous sodium thiocyanate. In wet spinning, the spinning solution is extruded through spinet into a precipitation bath that contains a coagulant, such as aqueous. Because the solution is extruded directly into the precipitating liquid, the process for making fiber is called wet spinning. Acrylic, rayon, and aramid and spandex can be produced by this process. The next one is dry spinning. Dry spinning is also used for fiber forming substances in solution. However, instead of precipitating the polymer by dilution or chemical reaction, solidification is achieved by evaporating the solvent in a stream of air or inert gas. The filament do not come in contact with the precipitating liquid, eliminating the need for drying and easing solvent recovery. The dry spinning process begins by dissolving the polymer in an organic solvent. This solution is blended with the additives and is filtered to produce a viscous polymer solution, referred to as dope, for spinning. The polymer solution is then extruded through the spinet as filament into a zone of heated gas or vapor. The solvent evaporates into the gas steam and leaves solidified filament, which are further treated using one or more process. Then I will describe melt spinning. In melt spinning, the fiber forming substance is melted for extrusion through the spinet and then directly solidified by cooling. Nylon, olefin, polyester, saran, and sulfur are produced by this manner. Melt spinning uses heat to melt the polymer to a viscosity suitable for extrusion. This type of spinning is used for polymers that are not decomposed or degraded by the temperature necessary for extrusion. Polymer chips may be melted by a number of methods. The trend is toward melting and immediate extrusion of the polymer chips in an electrically heated screw extruder. Alternatively, the molten polymer is processed in an inert gas atmosphere, usually nitrogen, and is metered through a precisely machined gear pump to a filter assembly consisting of a series of melted gauge interspread in layers of graded sand. The molten polymer is extruded at high temperature and constant rate through a spinet into a relatively cooler air stream that solidified the filament. Lubricants and finishing oil are applied to the fiber in the spin cell. At the base of spin cell, a thread guide converge the individual filament to produce a continuous filament yarn or a spun yarn that typically is composed of between 15 and 100 filaments. Once formed, the filament yarn either is immediately wound onto bobbins or is further treated for certain desired characteristics or end use. Melt spun can be extruded from the spinnert in different cross-sectional shapes: round, trilobal, pentagonal, octagonal, and others. Trilobal shaped fiber reflect more light and give an attractive sparkle to textile. Pentagonal shaped and hollow fibers, when used in carpet, show less soil and dirt. Octagonal shaped fiber often glitter free effects. Hollow fiber trap air, creating insulation and provide loft characteristic equal to or better than down. The next type of spinning is gel spinning. Gel spinning is a special process used to obtain high strength or other special fiber properties. The polymer is not in a true liquid state during extrusion, not completely separated as they would be in a true solution. The polymer chains are bound together at various points in liquid crystal form. This produces strong interchain forces in the resulting filament that can significantly increase the tensile strength of the fiber. In addition, the liquid crystals are aligned along the fiber axis by the shear force during the extrusion. The filament emerge with an unusually high degree of orientation relative to each other, further enhancing strength. The process can also be described as dry wet spinning, since the filaments first pass through air and then are cooled further in a liquid bath. Some high-strength polyethylene and aramid fibers are produced by gel spinning. Objectives of Kevlar and properties. Kevlar is a type of aramid that consists of long polymeric chains with a parallel orientation. Kevlar derives its strength from intermolecular hydrogen bonds and aromatic stacking interactions between aromatic groups in neighboring strands. These interactions are much stronger than the van der Waals interaction found in other synthetic polymer and fibers like Dyneema. The presence of salt and certain other impurities, especially calcium, would interfere with the strand interactions and has to be avoided in the production process. Kevlar consists of relatively rigid molecules which form a planar sheets like structure similar to silk protein. These proteins result in its high mechanical strength and its remarkable heat resistance because it is highly unsaturated as the ratio of carbon to hydrogen atom is quite high. It has a low flammability. Kevlar molecules have polar groups accessible for hydrogen bonding. Water that enters the interior of the fiber can take the place of bonding between molecules and reduce the material strength, while the available groups at the surface lead to good wetting properties. This is important for bonding the fiber to other types of polymer, forming a fiber reinforced plastic. The same property also makes the fiber feel more natural and sticky compared to non-polar polymers like polyethylene. In structural applications, Kevlar fibers can be bonded to one another or to other materials to form a composite. Kevlar's main weakness is that it decomposes under alkaline conditions or when exposed to chlorine. While it can have great tensile strength, sometimes in excess of 4 gigapascal, like all fibers, it tends to buckle in compression. Next is the super properties of Kevlar. The first property is it is strong but relatively light. The second one is unlike most plastic, it does not melt. It's reasonably good at withstanding temperature and decomposes only around about 450 degrees centigrade Celsius. Kevlar can be ignited, but burning usually stops when the heat source is removed. Very low temperature have no effect on Kevlar. There is no appreciable brittlement or degradation down to minus 196 degrees centigrade Celsius, which makes it excellent for Arctic conditions. Like other plastic, long exposure to ultraviolet light causes discoloration and some degradation of the fiber. Kevlar can resist attacks from many different chemicals, though long exposure to strong acid or base will degrade it over time. Kevlar remains virtually unchanged after exposure to hot water for more than 200 days, and its properties are virtually unaffected by moisture. There are some advantages of the Kevlar. It has higher tensile modulus than steel wire, high breaking tenacity, very high kinetic energy absorption, 4 to 5 times strength than tensile. It has a much higher tensile modulus than steel wire. But there are also some disadvantages related to Kevlar. and that are low elongation to break, low elastic conductivity, low electric conductivity, low thermal shrinkage. The uses and applications of the Kevlar includes military body armor and jackets. It is the first application or use of the Kevlar. Americans serving in every branch of the armed forces since the 1970s have depended upon the body armor and flak jackets made with Kevlar to help protect them from combat hazards such as ballistic projectiles and explosive fragmentation. Military body armor and flak jackets made with dopant Kevlar fabric is extremely lightweight and comfortable enough to improve mobility and reduce fatigue for soldiers in the field. Yet Kevlar fiber is 5 times stronger than the steel on an equal weight basis, offering superior protection against fragmentation and ballistic threats in military body armor and flak jackets. Kevlar is inherently flame resistant, providing thermal protection from fire. The second application of Kevlar is protection vest. Since DuPont first started helping protect officers with protection vest made with Kevlar, DuPont has been committed to developing new technologies to improve officer safety, from higher level bullets to knives, needles, and explosions. Protection vest made with Kevlar help protect against the ever increasing array of threats officers face. The third application is military helmet. Military helmet made with Kevlar meet demanding requirements for protection against a wide range of threats, including bullets, shrapnel, fragmentation. State of threat military helmet made with Kevlar, like the US Army Advanced Combat Helmet, absorbing 20% more kinetic energy than the personnel armor system for ground troops. Military helmets, they are replacing and offer protection from submachine gun bullet. The next application is automotive use. From passenger cars and light trucks to professional race cars, DuPont Kevlar brand fiber help increase the safety, performance, and longevity of automotive components. Several important components of new car frequently used item from the Kevlar brand of fiber. Kevlar can be used for a variety of automotive applications because it comes in a variety of product forms. Kevlar fiber is a continuous filament yarn available in a broad range of deniers. It is often woven into fabric and twisted and plied into cords. Kevlar stable and flock are short fiber versions suitable for textile applications and for reinforcement of thermoplastic and thermoset matrices. Kevlar pulp is a fibrillated short fiber widely used in friction and sealing applications. Kevlar engineered elastomer is a concentrate of short fiber material pre-dispersed in a thermoset or thermoplastic matrix. Kevlar also used in the following parts, in belts and brake pads. Brake pads made up of Kevlar pulp are better equipped to withstand the wear and tear that friction creates with their enhanced thermal stability and inherent abrasion resistance. Reinforced brake pads made up of Kevlar are designed for long life and safe quiet braking. Kevlar is also used in clutches. Kevlar is also effective in clutches which are subject to several frictional stress. Tests have shown that clutches lining with Kevlar do not require service or replacement as often as standard clutch linings. Gaskets. Due to its chemical and thermal stability, reinforced made up of Kevlar helps make gaskets strong and durable. Marine composite. Kevlar reinforcement helps reduce weight without compromising strength in marine, energy, and maritime vessel composite. The next application of the Kevlar is mass transportation. The remarkable performance characteristic of DuPont Kevlar helps enable manufacturers to build aircraft, ship, and rail cars that are lighter and more durable, resulting in increased fuel efficiency and lower operating and maintenance cost. Kevlar in aeroplane. Aircraft cabin flooring and interior. Aircraft cabin floors, overhead bins, and bulkhead built with DuPont Kevlar. Honeycomb cores have helped in weight saving for aircraft manufacturers. In addition to lightweight, honeycombs has very low electrical conductivity and high fire resistance, which help to contribute to addressing the safety standards the industry demands. The superior thermal and sound insulation also contribute to passenger comfort. Landing gear doors. Kevlar honeycombs help designers produce landing gear doors that are strong and light to allow for delivering more efficient aircraft. Wing boxes and control surfaces. The lightweight, lack of galvanic corrosion, and overall strength that Kevlar honeycombs help provide for wing-to-body fairings and control surfaces make it superior to the heavier, weaker, and corrosion-susceptible aluminum core that has been used in the past. Filament wound pressure bottles. Bottle containing pressurized oxygen on airplanes use molded casing made up of Kevlar. To help reduce the overall weight of the aircraft, an ordinary alloy encased bottle can suffer catastrophic failure, releasing metal fragments into the aircraft at high velocity, whereas a bottle using a casing made up of Kevlar may help risk ductile failure, rupturing rather than disintegrating, which does not result in fragmentation. Engine nacelles. The engine nacelles that surround jet engines must contend with thrust, lift, and vibration forces. Manufacturers choose to use Kevlar honeycombs core structure in engine nacelle because it is far stronger and lighter than earlier designs with an aluminum core. Engine containment rings. Many jet engine manufacturers add a protective layer of Kevlar fabric inside the engine cowl to help catch errant fan blades or massive broken parts flung outward by the engine's centrifugal force, thus potentially preventing them from damaging the wing or the cabin. Aircraft tires. Landing and takeoff cycles, friction, and rapid change in temperature push aircraft tires to their stress limit. Tires reinforced with Kevlar brown aramid fiber help provide enhanced toughness and thermal stability. Rotor blades. The alloy cores that historically predominated helicopter rotor blade designs are giving way to composite, of which honeycomb core made up of Nomex or Kevlar is proving to be a material of choice. Modern helicopters are redefining efficiency and performance with lighter, stiffer rotor blades made up of Kevlar. The Kevlar is also used in spacecraft. Kevlar fiber has proven that it is strong enough to survive the extreme force and temperature fluctuation of space travel. When the Mars Pathfinder landed on the surface of Mars, Kevlar fiber reinforced the inflatable landing cushions and the ropes that secured them, helping the Pathfinder to complete its 40 million mile journey fully intact and ready to explore the planet's surface. Kevlar is used in communication satellites and also in the space shuttle to help protect against impact from orbital debris. Other uses of Kevlar include the off glove, air pack harnesses, Kevlar in fire-resistant mattresses, sport equipment, ropes and cables. Finally, we will conclude this topic by some sentences. These are Kevlar is primarily used for two performance related reasons. It is portable and simple to incorporate. Everything from seismic shear walls to bank counters can benefit from the structural strengthening or plastic protection provided by a thin blanket to reduce weight and increase strength in carbon composite. Add the fibers. The lightest and most durable type of Kevlar are grades 49 and 149. Kevlar 29 is as strong as glass fiber but is lighter. Kevlar is still pricey, thus prices need to be decreased. Thank you so much. These are the references from which this material has been collected.